All right. Okay, we had a packed lab. I just want to remind Wednesday group, please come on time, a little bit ahead of time so that you can put your lab coat on and get started with lab right away. Yeah, I think half the class is not here yet, right? Yeah. So yeah, we finished like 12:35 or something. Anyway, so let's get, I don't know where we are. I've had a long day. Anyway, let's try to remember where we were all together and continue. I think we were talking about resolution last time. So hopefully some of you get a chance to actually review over the weekend for the quiz coming up. So what is peak resolution? I forgot my chocolate. I still have that box. It's just, Anyway, I'll bring it next time. Nick.
How sharp the peak is, whether or not those match with one another?
Perfect. In simple terms, how sharp the peak is, and the sharper it is, the more the chances of separating it from other components. Okay, so resolution is basically resolution of compounds or separation of compounds from each other. Okay, what is a solvent front peak? Those that were in okay, go ahead.
That's when the mobile phase reaches the detector.
When the mobile phase reaches the detector from the time of injection. From the time of injection, the mobile phase is going through, and it's going through the void volume of the column. So when it gets to the detector is going to say, oh, something hit me, and it's going to give you a signal. And that would be your solvent front peak, which is also the void volume peak. So it means the same thing. What is the difference between retention volume and retention time? Go ahead.
Retention volume is how much of the mobile phase you can tell all the cylinders.
Yeah.
Retention time is how long it takes for all the cylinders to.
Perfect. So the retention volume is the amount of solvent, the volume of solvent or mobile phase it took for a particular solute to come out, whereas retention time is the amount of time or the time needed for that particular solute to come out. And in chromatography, we often refer to retention time more than retention volume. What's the relationship of peak width to resolution in terms wider width, you get better resolution, or narrower width, you get better resolution? Nico?
Narrower width is better resolution.
Okay. What's this first step in developing a separation between solutes of interest in your sample? What's the very first thing you will do to get a separation? See what other people have done. See what's published, what's out there, and if you, which is very rare that you don't find published work related to the work you're doing, but just in case you're starting with a total unknown like forensics, what Gary was talking about last time, bring a piece of the wall to see what's going on or what's growing in there, and then you would just have to start somewhere. In gas chromatography, start with a nonpolar stationary phase. In liquid chromatography, try to hypothesize what the compounds are. You think are going to be polar, nonpolar. You can start somewhere with a stationary phase and a mobile phase and go from there. Okay, so we stopped here. I just want to remind you before I go into this that we are looking at the three functions of resolution: efficiency, selectivity, and capacity. So the efficiency of the column, the selectivity of the column, and the capacity of the column all are, or the resolution is dependent on all of them. And we're starting to talk about efficiency of the column. We talked about theoretical plates last time, and then I described what height equivalent of a theoretical plate is. So this takes into account the length of the column. So instead of looking at only the number of theoretical plates, then you look at the actual height of the theoretical plate. And theoretical plate is basically the location or the equilibrium that happens between the solute as it goes from stationary phase to mobile phase. The quicker it reaches equilibrium as it goes down, the narrower or the shorter is the height equivalent of theoretical plate. If it takes long time to equilibrate, it's going to move down by diffusion rather than going in and out. Then this broadens your peak, and this leads to long height equivalent theoretical plate. So the number of theoretical plates, if you remember from last time, the higher the number of theoretical plate, the better is the resolution. So I drew that last time. Just want you to remember this before moving on. So you start off with a column that has high efficiency, and you have a number of equilibriums that happen as the solute goes down your column. So it equilibrates. The more segments of equilibration there is, the better is the efficiency of the column. As the column ages and loses capacity and loses functional groups, what happens is your sample takes longer time, your solute, to elute or to reach equilibrium. So this height increases. So that's the height equivalent of a theoretical plate. So it goes from here to here over time. Then you're losing efficiency. So here you have a really sharp peak because it's not diffusing within the column, but here you have this really broad, bad peak. Okay? So the shorter, the better. Bigger, not good. So when we know this, then we look at the relationship of different factors that impact the height equivalent of a theoretical plate. So U here stands for the flow rate of your mobile phase. And then in the equation up here, you have three factors, which are important factors. I don't know if you heard about them before, but A is Eddy's diffusion. B is longitudinal diffusion. And C is mass transfer, or the time that it takes for the solute to reach equilibrium. Okay, so let's talk a little bit about what A is. So I'm going to illustrate that by a little bit of drawing. Let's say you have a column or a river. Start with a river. And you have big stones in a river versus another river, you have smaller stones, pebbles. And then you have the water flowing. So if the water coming in hit a big stone, do you think you'll have more spread of the water, like different spreads? Or will the water just continue in one path versus here, going down or splitting? In which case you'll have more streams of the water splitting. No. When it hits the big stone, the water starts going around it, over it. But here, it's very small pebbles, so your stream is not really changing much of a direction. So same with a column. So if you have a column with large packing, large particle size for packing material, you have multiple streams. So your compound or your solute of interest will go in multiple ways. and that will delay it on the column. So this will result in a wider peak. When you have smaller packing material size, then you don't have much of a diffusion or going into different streams. It's just you have limited number of streams that the particle can go in. So you have less diffusion within the column, but more in and out diffusion, or in and out movement rather than diffusion. And then your peak will be narrow. So that value, the higher the value of eddy diffusion, the more you have diffusion and movement in different streams, then you have higher height equivalent of a theoretical plate. So here is to illustrate that the packing or your stationary phase particle size has a huge importance or has a huge impact on resolution. So the smaller the particle size, the better is the resolution. Okay? The more packed they are, the less void there is between the particles, the better is the resolution. Okay, so longitudinal diffusion, this is basically the diffusion within, going from highly concentrated to less concentrated, going downward through the column compared to going into your mobile phase. So equilibrating between stationary phase and mobile phase is one movement. Another movement is diffusion, going down by diffusing. The more the particles diffuse or the solute diffuse, then you also end up with wider peak. Now this factor over here is dependent on the flow rate. If you have really slow flow rate, so your mobile phase is going down slow, then this will cause more diffusion downwards rather than equilibrating between the mobile phase and the stationary phase. So that's why it's an inverse relationship. That's why if you have low mobile phase, you have a bigger B value, then you have a bigger longitudinal diffusion, then you will have higher height equivalent of theoretical plate. So that's why flow rate is very important, because you want a little bit faster flow rate so that instead of diffusing downward like that within the column, within the stationary phase, it would go in and out with the mobile phase. But you don't want it to be too fast. So again, there is an optimal flow rate, because if it's too fast, it's going to impact this factor, the factor of the mass transfer factor. So the mass transfer is the time it needs to reach equilibrium. So all of these are equilibrium sites on your column. How long it takes to reach equilibrium is important. So the quicker it reaches equilibrium, the shorter is your height equivalent of theoretical plate. However, if the flow rate is so high, you won't get to an equilibrium. There will be no time to reach equilibrium. That's why it has an inverse effect. So flow rate, it doesn't go always in one direction. Increasing the flow rate up to an optimum is what you need to find out. Which one is your optimum, where you reach equilibrium and you have minimal diffusion through the column. Okay, so what makes the C value small is something I think Gary talked about a little bit. When you have a capillary column, which is a hollow column, in GC, where you have the coating is on the sides of the column. In HPLC, you can have a peculiar column. You can have capillary, but you can also have a different type of column where you have an inert stationary phase. Well, inert support. That means it doesn't interact with anything. And on the outside of that inert support, you have a thin layer of your stationary phase. So the reason of the thin layer and the benefit of a thin layer is you reach equilibrium really, really fast. There is no diffusion. There's barely any diffusion. There is minimal stationary phase, so it will go in and out very quickly. So the C factor becomes really small when you have a capillary or a peculiar column. So the faster you reach equilibrium, the better it is. Basically, the better is the resolution, the sharper is your peak, and the less is the diffusion. Any clarification on this? Anybody would like me to repeat anything? Yes? The B? The B factor, yes. So here we talked about longitudinal diffusion is the B factor. So when you inject your sample, it starts off as a thin layer on top of your column, on top of the stationary phase. It starts thin, and then diffusion is you go from concentrated to less concentrated area. So it will automatically start diffusing, going this way. That is longitudinal diffusion. But at the same time, you have your mobile phase going. So the mobile phase is going to go by, and then your solute is going to go in and out, as well as going from concentrated to less concentrated down the column. Okay? So if you have a very low flow rate, then you'll have the movement is going to go more longitudinally rather than going in and out and going down. You want it to go in and out and reach equilibrium. That's how you get better resolution. If it diffuses, then your band grows from this to this. Then your sample is distributed like that, instead of staying thin line, thin band, and going in and out and moving down as a thin band. This will result in a really wide peak. This will result in a sharp peak. Yeah? Good. Any other questions? Yes?
So you said the quicker it reaches equilibrium, what happens to reaching it's
Smaller, yeah, yeah. Because all of these are segments of equilibration. Those, the N, the height equivalent theoretical plate, is an equivalence of reaching equilibrium between the stationary phase and the mobile phase. Other questions? Okay, so we learned about the flow rate effect. There is the temperature effect. So the temperature effect, we talked about it a little bit last time, is when you have a little bit higher temperature, your viscosity of the mobile phase becomes lower. And with viscosity becoming lower, you will have better movement. And also you would have higher movement of your solute. So you would reach equilibrium faster. So also oftentimes we regulate temperature in LC world, not only in GC, but in liquid chromatography, we increase the temperature a little bit to enhance, reduce the viscosity of the mobile phase and enhance the movement, quickening the movement of your solute. But again, there is an optimum. Like the flow rate, there is an optimum. You cannot just say, okay, I'm going to keep continuing to increase my temperature. I will reduce my analysis time. Life will be good. No, we can't do that, because if you increase the temperature, first off, you might hurt the column. The stationary phase itself might not be stable to high temperature. Second, you will have really fast movement. You won't get that much equilibrium. Or if you reach equilibrium, another problem becomes that the solutes come out very fast and they will not separate from each other. So you actually lose resolution because you're not giving them enough time to interact with the column and be delayed. You want them to be delayed a little bit so that they get separated. Okay. So the second factor in the resolution equation is the selectivity, how selective your column is. And really this has to be, it's depending on what functional groups you have on your column. So if the functional group, if you choose really hydrophobic, let's say you're doing reverse phase chromatography and you chose a C30, which is really hydrophobic column. So if you want to separate compounds that are not very hydrophobic, they have some sort of polarity, you are not going to get separation. So you really want to select your selectivity based on the compounds you have. So how selective you want your stationary phase to be to your compounds. And the mobile phase, you can change the nature of the mobile phase by increasing the strength of the mobile phase, depending on the type of mode of separation you're having. So either increase polarity or decrease polarity or increase pH, increase salt concentration, and so on. So by changing the nature of the mobile phase, you change how the solute is interacting with your functional groups. So you are changing the selectivity. And again, the selectivity, it is represented by the corrected time, retention time of peak 2 over the corrected retention time of peak 1. And it's corrected because it's corrected for the void volume. So the void volume or time of the solvent front is taken into account. So, and this gives you the relative distance basically between peak 2 and peak 1. The higher the alpha, the better is the resolution and the selectivity, obviously. But when the alpha is 1, for instance, that means you have an overlap and no separation and no selectivity between the two compounds to the column or the stationary phase. And selectivity in chromatography is one of the most important factors, even more important than resolution, because it is directly related instead of quadratically related to the resolution. So that's the capacity selectivity factor, whereas the efficiency is the square root of n divided by 4. So this means the selectivity of the column is more important than the number of theoretical plates. Because if you don't have selectivity, there's no resolution. Sometimes even if you have wide peaks due to smaller n, but you can still get 2 wide peaks. You can still get them resolved from each other. It's okay that they're wide, but they are actually resolved due to the selectivity of the column. So that makes selectivity more important than efficiency. The last factor is capacity. Any questions on selectivity? Okay. The last factor is capacity, and this has to do with the number of functional groups on the column. Over time, the column, you might hear the term stripped. The column was stripped. That means some of the functional groups stripped off. Due to excessive use, you lost some of your functional groups. When you lose some of your functional groups, you have less interaction with the column. When you have less interaction with the column, your retention time becomes shorter. So solute A, instead of eluting at, let's say, 10 minutes, it's eluting at 5 minutes. So it went backwards. And then by going backwards, then it's going to hit another solute, and then they will not separate. B already had low selectivity to the column, and B was already eluting faster. And then when you reduce the capacity of the column over time, then A is also going to elute faster, and then you lose selectivity. You lose resolution, sorry. And it is determined by the K prime, which is the retention time of the solute minus the retention time of your void volume, or minus the time for the solvent front over the time of the solvent front. So as the retention time becomes closer to the solvent front retention time, then your K prime becomes smaller. That means you have less capacity. Okay. So In chromatography, you have two types of analysis, qualitative and quantitative. So in qualitative analysis, what are you really trying to do when you are doing chromatography for qualitative purposes? Kim? To see if it's there. That's one form of qualitative analysis. What else?
Maybe looking at like the shape, the overall shape and how many peaks there are.
Okay, how many peaks there are? That means how many compounds do I have? Yes, so how many different compounds do I have in the sample when I extract with solvent X? Yes, good. And then to see if it is there. What else? Sometimes yeah. Yes. Thank you. That's the thing I was looking for. Yes, to identify. So sometimes it's just running and trying to identify what there is. Not necessarily quantitate, just to try to see what kind of pesticide do I have in my sample? What kind of phytochemical do I have in my sample? Okay, so that's qualitative analysis versus quantitative, where quantitative we're actually looking not just only to identify and find out if they're there or not, but also to quantitate, to determine an amount or a concentration. And that's what you did in the, one group did in the caffeine lab today. So qualitative analysis, there are different ways of doing qualitative analysis. The first thing you would do is look at the retention time. So you run a standard. We did that in the caffeine lab. Run a standard, look at what time that caffeine comes out, and then search for that time in your actual sample. Look at the peak that elutes at the same time as your standard. That's the weakest form of qualitative analysis because you're assuming that there's nothing else in your sample that's going to come out at the same time as your standards. But it is one form. Spiking of a sample. If you don't have an actual, you don't want to run a standard and you have, well, you can run a standard, but if you have two peaks that are very close from each other and you want to know which one is which, then you can add to the sample the compound that you think you're looking for, or the compound that you're looking for. And then you will see which peak increase in size in your sample. That's what's called spiking, is you actually add to your sample and run it with and without spiking to see which peak is going to increase in size. Photodiode array detector, and I talk about it more in detail in the HPLC and in the spectroscopy lecture. It's a type of detector that is based on absorption of light. And one of the groups today, or two groups in lab, we talked about that. It's a type of detector that allows the production of a spectra, which is a scan of wavelength and absorption. So I'll talk about the physics of it later, how it works, but now I'll just show you what a spectra is. A spectra is when you plot, let's say in this case, absorption over wavelength. Lambda stands for wavelength in nanometer. And if we're doing UV, it will be somewhere between 200 and 400. And then what happens in 0.1 seconds, every 0.1 second, whatever is going through the detector is being recorded. The data is being recorded, or the absorption is being recorded over a range of wavelengths. So let's say you have no absorption at 200 nanometer, and then as you increase the wavelength, you start seeing some absorption, and then later on you don't see any. So it seems like you have maximum absorption, let's say here. This is, let's say, lambda 256. So here it's telling me at 200 there is no absorption, at 220 there is no absorption, and then at whatever 240 my solutes start to absorb light, and then it absorbs maximum light at 256. So I'm going to call this lambda max. Lambda max means the wavelength at which I have maximum absorption. So this is unique for X. Y could be like that, with lambda max at 320. So every compound, in theory, if they are absorbing light, they will have a unique spectra, or we call it a fingerprint. The photodiode array detector allows or give you an output where you can see a spectra, and then you can identify or differentiate your compounds based on the wavelength. Sometimes in your sample, you have different compounds with different signals or detection methods. So you can use a UV coupled with a light scattering detector, for example. And I'll talk about the light scattering detector when I talk about detectors of HPLC. So you can combine or put detectors in sequence and get as much output as possible so you can get an identification of what you have. So you can get better. If some sample absorb light, some compounds absorb light at the same wavelength. So if you put another detector next to it, then it will have a different signal. Then you can differentiate them that way. Sometimes you take the ratio at two different wavelengths. So you measure if you have compounds that absorb similarly at similar wavelengths. If you take the ratio of like at 280 over absorption at 220, say, and then you can differentiate two compounds from each other because they will not have the same ratio. Very rarely they would have the same ratio. Separation using another chromatography mode. So if your first dimension did not give you a separation, you will use another dimension. And this is very common in protein analysis, where you separate by size, then you separate by charge, then you separate based on polarity. So you can purify that way. Because proteins have, some of them have the same molecular weight but different charge. Some of them have similar molecular weight and charge, but they probably are different in polarity due to the different amino acid polar and nonpolar regardless of charge. So in proteins, you can use that to separate them better and identify them. A more powerful technique for identification is mass spectrometry, where you actually get the molecular mass. Okay. All right. In quantitative analysis, you have to determine a quantitative measure. So you need to obtain a measure that you can use to quantitate. And oftentimes what you look at is when you have a chromatogram, you have peaks, right? So this is the output you have, chromatographic peaks. So how do you use them to quantitate? So you look at the peak and you go, okay, so there is a peak height, and you can actually get a peak area. In quantitative analysis with HPLC or even GC, we often go with area. Why is that? I will illustrate. Why do we often go with area? It's because the height is subject to the resolution of the column. So you have this peak, nice and sharp. It has this particular height. And then over time, if you lose resolution, the same compound is going to give you this peak. But if you take the area here and the area here, it will be the same. But the height is different. the height is impacted by resolution and the selectivity of the column and the capacity of the column and so many different factors. Whereas the area, no. You will always have the same area unless something's wrong with your detector. So that's why we always go with area under the curve, and there are programs that will generate the area under the curve for you. You don't have to use any strip chart recorder like in the past. Or in the past also they used to cut the peak, print it out and then cut it and weigh it. So no longer. You can have programs that will smartly determine the area under the curve for you. But this is not the end of the story. You get the area under the curve, and then what do you do with it? And I'm going to introduce something that has always been confusing to students, and they almost always don't get it. Either I don't do a good job, which basically that when almost always they don't get it, that means it's my problem. So it's my fault. So I'll try to explain it a little differently this year. Okay, so to quantitate, you need to have standards and run calibration. We already talked about that. So you need to produce a standard curve. And the way you produce a standard curve is you basically prepare standards at different concentration. You obtain pure standards and you physically prepare them at different concentrations, and then you run them through your system and you get the area of the peak for that standard. And then you plot the area over the concentration, and then you get the equation of the line and you use it to predict concentration in an unknown sample. Where you have the unknown sample, you run it through, you get the area, and then you plug it in your equation and you get X, the concentration. Very simple. What do we call this type of calibration or standard? Is it external or internal? Just by logic. External. That is external. External standards are used to quantitate, to produce a standard curve. All right, very good. I always need external standards to quantitate. Now, do I always need internal standard to quantitate? No. But it makes my quantification that much more accurate. So what is an internal standard? So I always keep that in mind. I never said this before, but now I'm saying it. External standards are always needed for calibration and quantification. Accurate quantification, complete quantification. Okay. Now internal standards are not always needed. They are not really needed for quantification. They are needed to enhance accuracy and precision. Okay. Let me tell you what internal standard is. So an internal standard, I don't have it written here. An internal standard is a standard that has similar characteristics to your compounds, but does not elute at the same time. That means that do not come out at the same time. So here's an example. There's sugars in molasses. There is no lactose in molasses. Lactose is dairy source. So if you add lactose to your sample, it doesn't come out with your glucose or fructose or sucrose. It comes out separately. So important characteristic, it's similar to your compound so that you can see it in the same run. You don't have to do anything special. And the other thing is you don't want it to come out at any time point as the others. Okay, so it is similar, but it does not come out at any time point with your samples. Why do we add it though? Why do we add an internal standard? The benefit of an internal standard is that when you're preparing your sample, some of you today did the GC analysis, and you saw how you prepare free fatty acids, and it has a lot of, what do you call it, steps. So you have to do a lot of steps, and there are a lot of steps. That means there's a lot of chances of error during sample preparation. If you were to add an internal standard, you would add that internal standard to your sample, and you add it to your standards as well. And that internal standard is going to go through the process, the same process as your sample. So if you lost a sample, if you had some error and had some losses, that is applied to the internal standard as well. So that helps with better precision and better accuracy. And why is that? Because you have your internal standard. Say this is going to illustrate here. You have your standards, external standards, and you have your sample in a flask. Sample. You add to the external standards and to the sample, you add your internal standard. So all of your external standards, different concentrations, and all of your samples get the same amount of an internal standard, same volume, same concentration of an internal standard. So it goes in all of the standards and it goes in all of the samples. You need external standards. You can't quantitate without external standards. Don't get me wrong. You need it. Okay. And then here's how you plot. So each of these lines are standard curve for a certain component. So you are looking at 3 fatty acids, let's say. So the X, Y, and Z fatty acids. So each one of them you have to plot a standard curve for using external standards. But you have internal standard in there. So the way you plot is you put the concentration of your external standard. So here, the x-axis is concentration of your external standard. And the y-axis is the absorption of your external standard, or area, sorry, area of your external standard by the area of your internal standard. So you have, let's say, glucose. So you take the area of glucose by the area of the lactose. So the ratio of the areas. So you always take the ratio of the areas at a particular concentration and you plot that. You get equation of the line. And then in your sample, you also get the ratio of the area of that particular solute over the area of the internal standard, and use that as a y to solve for x in your equation. Okay, so basically by doing the ratio, you are correcting for any error that comes from sample preparation, or in GC, for example, from volume injection. If you're doing a manual injection in GC, it's prone to error. But then the internal standard in your chromatogram has gone through the same process as your sample. So when you correct for that, you correct for that error. Okay. Yes, Zach?
Could you go back to the beginning? So you said internal standards are not always needed for quantification, but they're needed for what?
The internal standard?
Yeah.
They are needed for enhancing precision and accuracy because they go through the same process of preparation as your sample. So if you have any errors or losses during sample preparation, internal standard is what can account for that. So enhancing accuracy and precision is the job of your internal standard. Okay. Yes, Nathan.
Why does going through the same process as your sample and external standard, like enhance precision and accuracy?
What?
I know you just explained that. But
So say that again.
why does your internal standard, when it goes through the same process as the sample and external standard, why does that enhance precision and accuracy?
It enhances, okay, because it's in your sample. Say that you put your internal standards in your sample, and then the sample went into the water bath to evaporate, and then something spilled there. So you lost, your concentration has been suffered a little bit of your compound of interest. But the internal standard also got the same treatment. So the same proportional loss happened in your sample solute and in your internal standard. So when you correct for that, when you take the ratio, it corrects for any spills, for example. Yeah? Good. Yeah, yeah.
So for in this example, you're saying the external sample or standard would be the like glucose. Is that
Yes,
like
exactly.
a regular like standard glucose
Yeah.
that's not in this sample?
Exactly. So yes, so when you are looking at sugars in molasses, you go and get glucose standard, pure glucose, pure fructose, pure sucrose, and prepare them externally from your sample, and prepare them at different concentrations. Yes?
You always get an internal standard, like every time
You don't have, okay, so internal standard are not often always used, but it's preferable that you use them. But it's an extra hassle to actually find a compound that is similar to your compounds and does not elute at the same time. So it's not always easy to find an internal standard. Okay, good. I hope you all know how to differentiate this year from external and internal standards. All right, so I'm going to stop here. Wednesday is your quiz. One of the TAs will come and give you the quiz. I won't be here. And the Wednesday group, don't miss me too much. I won't be in lab either. But Friday, Gary's going to continue with the GC lecture and an MS on Monday. And then I will continue with HPLC after that. All right.